Okay, we're going to get started with the lightning session. Welcome again, and this is probably one of the most interesting sessions. This is the first time we're doing it at ICS, I believe. We've done it at many conferences before, but this is kind of like an abstract of the conference, where you'll hear 1-minute talks for each paper, except for 2 who cannot be here for the lightning session. So it'll be a fire hose of 41 papers presented back to back. And we'll start with the first one now.
Alright, so yeah, today I present poly-ACC. That's our work on transparent compilation to heterogeneous hardware. The idea is basically very simple. So we just take existing sequential software and we want, this makes too much noise, and we want to find a way to automatically map it to the multi-core CPU and especially to a multi-core accelerator. And the idea here is really we want to model a vectorizing compiler but make this available for like accelerator programming. We have 3 main goals. We want to make this automatic, we want to make this execution time regression free, and we want to reach high performance. We want to optimize for the memory hierarchy, exploiting GPU shared memory. We want to establish a heuristic that allows us to decide if a kernel is worth mapping to the GPU. And we will evaluate our work on a set of benchmarks, including 2 spec benchmarks. And for Cactus ADM, we will show that our performance is twice the performance of the best thread parallel code. I believe that this work will simplify accelerator programming and will free developer resources to work on more difficult mapping problems.
So I'd like to ask the speakers to get closer to the microphone because they indicated they cannot hear it in the back. So make sure you're closer.
Hello everyone, I'm Liu from Purdue University. So Tutorial is widely used in many aspects, such as data mining, simulation, and retracing. However, Tutorial is highly input dependent. Different also may access a different part of the tree, which will result in control and memory divergence. A good scheduling can greatly reduce this divergence. But finding out optimal scheduling is an NP hard problem. In our work, we come up with a hybrid inspector-executor-based scheduling algorithm. Say in this example, in original schedule, different threads in the same work may access different part of the tree. GPU will actually serialize them and execute them one by one. In our schedule, we can group threads with similar behavior together, so GPU can execute them simultaneously. Through our evaluation, our technique is around 6 times faster than the baseline and 1.4 times faster than hand-tuned method. To see more details, please come to my talk at 11:50.
I'm Siddharth from IIT Kanpur. Our work is on heterogeneous CPU-GPU, single-chip CPU-GPU heterogeneous processor. In such an environment, when both CPU and GPU execute at the same time, both of them degrade due to mutual interference. Statistically, on our workloads, when CPU and GPU execute, compared to the heterogeneous setup, when CPU and GPU execute standalone, CPU improves by 35, 35, and 26, and GPU improves by 21, 30, and 54%. We tried to reclaim some of this lost performance by designing a novel LC management policy which measures reuse probability of CPU and GPU block using a working set sample cache. Our policies are designed so that we are able to learn long distances and avoid any bias due to large GPU working set size. We are able to improve these major reuse probabilities are used to design an LLC management policy. We are able to improve CPU performance by 2, 4, and 7%, and GPU performance by 8, 9, and 12%, while we are able to reduce LLC miscounts by 13, 12, and 13% for 1 to 4 core CPU and GPU configuration. Thank you.
Hi everyone, I'm Dave Liu. As we know, energy optimization solutions may come from different layers of the compute stack. The theme of our work is we need a better coordination between layers. Imagine you have a solution, energy management solution from the higher layer. And in other words, you want to take advantage of application-specific traits to make energy optimization. And this solution probably works well with your application A, which deployed on a 2-core CPU. And it says that the first core should run on 3 gigahertz, and the second core should run on 1.4 gigahertz. Everything is perfect, except what if you have multi-applications co-run? In this case, application B actually wants to make conflicting requests of DBFS. So how to be effective? And our solution is an energy management coordination system to turn this greedy energy management into an egalitarian coordinating runtime. Thank you.
I'm Dimitrios. So due to manufacturing issues, in the manufacturing process, modern day CPUs sometimes have different power consumption, which in power constrained environments can translate to different performance. This causes a new form of heterogeneity, which typically can be dealt with load balancing. But load balancing sometimes may not be sufficient due to synchronization like barriers. So what we found out is that we can mitigate this problem by redistributing power between sockets on the same node, and also by disabling some of the cores. Doing this statically, finding that for the optimal configuration is difficult. So tune in later on to see how you can do this at runtime in a single run. Thank you.
I'm Bilge from University of Illinois. My talk is about variation among processors and supercomputers. We use compute-intensive kernels to analyze the variation in four top supercomputers, Edison, CAB, Stampede, and Blue Waters, using up to 16K cores. As the figure shows, we find that there's 16% variation on turbo boost-enabled supercomputers. We analyze temperature and power measurements of the processors and find that the intrinsic differences in chips' power efficiency is the reason behind these variations. The variation can lead to unpredictable and suboptimal performance of tightly coupled HPC applications. So we suggest ways to mitigate the performance variation, such as dynamic load balancing.
Good morning, I'm D.K. Panda from Ohio State University. The focus of this work is trying to combine high-performance computing and big data. And especially as we are seeing the NVM, which is becoming very important these days, how the big data computing can be really accelerated here. And the main thing is the Hadoop distributed file system, which is the file system on which a lot of Hadoop, MapReduce, Spark, HBase, all those environments run. So we are trying to combine this NVM and the RDMA, which is there in the InfiniBand, together to design a new file system, which is, we call it NVFS. And within that NVFS, we have designed alternative designs with different kinds of data movement from the DRAM to NVM, NVM to NVM, all those different designs we have explored. And then here we are trying to show for a different kinds of workloads, we are able to get up to factor of 4 improvement. Here a Spark page rank almost a 24% reduction in execution time. Thank you.
Hello, this is Amro. Today I will be presenting route-aware management of NVM-based memory extensions. So DRAM is no longer easy to scale down, and there are already emerging NVMs, which is promising for replacing DRAM. They are fast, dense, and non-volatile. However, NVMs have slow and limited number of writes. There are several ways to integrate NVMs or deploy them in the memory system. And this talk we will be looking at using NVMs to extend the memory. Specifically, we are looking at using NVMs as memory extensions, where you have the DRAM and NVM, and access to NVMs will be handled by the OS and moved to the DRAM and mapped in the process. In our study, we will be looking at how much performance degradation do we get from different DRAM NVM ratios. how long do they last, and how can we reduce the number of writes, and how to improve performance. Thank you.
Hello everyone, my name is Yang Hu. I come from the University of Florida. Recently, the unified virtualization platform has evolved into a new concept, software-defined data center. The software-defined data center relies on many important background services. We term these services as management workloads. However, we find that management workloads bring tail ending issues. To be more specific, if a management operation involves several physical nodes, a slowdown on one node may contaminate other involving nodes and incurs more energy consumptions of other management operations on them. Towards this issue, we build tail energy models and propose a graph-based analysis scheme. Evaluation results show our system whole can efficiently reduce tail energy and improve the system energy efficiency. Welcome to my talk.
When you get off the stage, actually, you can hit off the button so that it displays the next talk. That's fine.
Good morning, everyone. I'm No Liu. Today I will present this paper, Proposing an Adaptive Multi-Power Source Data Center. This paper focuses on how to leverage multi-power energy source to efficiently power data center. Firstly, I will present the power distribution architecture for data center, which include the conventional power distribution architecture and the emerging multi-power source power distribution architecture. Based on the power distribution architecture, we will propose a learning-based intelligent multi-power source management, which include modeling, training, learning, and configuration. That's all. Welcome to my session this afternoon. Thank you.
Good morning. My name is Haoran Cai. As power mismatching between power demand and green power supply is one of the biggest challenges for building green data centers with new and clean energy. Power demand from servers in data centers are actually ineffective since typical servers are generally powerful but energy efficient. So a proposed Green Deal strategy, which incorporates WIMP servers into green data centers with the support of new architecture and specific control schemes. The results show that heterogeneous servers can achieve 100% power mismatch and renewable energy utilization. Also, they can improve battery lifetime by 2 times. Okay, thank you.
Hello everyone, I am Hamida Sultan from IIT Delhi and my work is on noise-aware scheduling in data centers. So as more and more workloads go inside data centers, they are becoming louder. And there are several possible circumstances in which employees may have to work from within a data center. So the high noise level adversely affects their productivity and hearing. So we propose a solution through workload scheduling, and with simple heuristic-based solutions, we have been able to obtain a reduction of 13 dB in noise with a cost overhead of less than $30 and a timing overhead of less than 1%. Thank you.
Hello, my name is Mark. I'm going to talk about fast multiplication in binary fields on GPUs. It's going to be the last paper of today's sessions. The primary optimization technique that we are offering here is register cache. It's going to replace the use of shared memory in GPUs by registers. And the really important part is that it eliminates or reduces shared memory traffic, improves performance, and is applicable to many applications today. What we're showing is the real, pretty complicated kernel that achieves very significant boost in performance by using this register cache optimization. And overall, it is faster by 2 orders of magnitude than the hardware-optimized, hardware-accelerated CPU version, which is pretty remarkable, and I really recommend you to attend this session. Thank you very much.
Hello everyone, my name is Guoyang Chen from NC State University. So as we all know, GPU is often equipped with a complex memory system where to place the data for each object is very important to the performance of the program. Previous research have observed 3 times performance difference among different data placements. So all previous research only place each data object in one type of memory, which we call it a single view. And what we are going to do here is create multiple views of each data object and place it on different kind of memory. And for each reference, you can just choose one view to access. And among these views, we do not need the coherence here, and which is very interesting here. And so the key contribution of this paper is to identify the safe scenarios of multi-view without coherence needed. And then we enhance the data placement using this multi-view. Here shows the good results with very little runtime overhead and small space overhead. Thank you.
Good morning, my name is Zhang from Eindhoven University of Technology. Approximate computing is a technique that sacrifices accuracy for substantial performance boost and power reduction. The state-of-the-art design focuses on data on error-tolerable, data-intensive applications, but there is still high demand for traditional scientific applications. In this work, we focus on the long-ignored approximates units in GPUs, the special function units, and clarifies unique role in performance boost and power reduction. We propose a transparent, trackable, and portable framework to achieve the best performance and reduce power. It requires no modification to the application or the hardware. So please come to my talk at 11 tomorrow. Thank you.
Okay, so this is work from Ohio State that I'll be presenting on behalf of my students. And this work is driven by the observation that SIMD instruction sets have evolved. They have support for gather-scatter operations, which means you can try to take data which is not necessarily contiguous, but from performance viewpoint close to each other, and still try and support SIMDization. So this gave us an opportunity to look at irregular applications on SIMD. And this work here is a follow-up of a paper we had in CGO, where we designed an inspector-executor method to try and map irregular reductions and graph algorithms onto SIMD instruction sets. Now this paper is completing the picture by looking at situations where edges are changing or the grid is evolving, and essentially we can think of as an incremental inspector-executor that we are going to present here. So that's tomorrow.
So when you get off before you get off the stage, if you click once more so that the next presenter's slide is displayed, that would be best.
Hello, this is Dida Munat from Koç University. I'm local here. So I'm not listed as a co-author because I'm presenting on behalf of the authors, and they couldn't attend because of some visa issues. So as you know, HPC applications, debugging HPC applications can be very difficult because of the large number of threads and also because of the non-determinism inherent in the execution. Because of the non-determinism, you may not be able to detect the bug at different runs. The authors proposed a record and replay technique for one-sided communication. That's a novelty in the paper. The previous work focused on a shared memory or distributed memory system, but this one focused on one-sided communication. So the technique has 3 parts. First, recording the execution, and then the offline processing, and then the partial replay. The results, they don't introduce much overhead because the runs are performed on a subset of the threads, which only use 1 to 30x overhead onto the application. That was it.
Hello, I am Konstantina from the University of Cambridge. As we all know, software queues are very slow. One of the reasons is that the enqueue and dequeue functions have many instructions, From all those instructions, we actually need only 2 instructions, one to store the data into the queue and one to increment the pointer. In this work, we address this problem and we propose a new software queue with only 2 instructions overhead. As a result, we increase the throughput by up to 57%. So if you want to learn more about links and how we managed to reduce the overhead down to 2 instructions, you can come to my talk on Thursday at 11 in session 5B. Thank you.
Hello everyone, my name is Yao Yuanyao, and we'll be providing our paper in the timestamp-based cache coherence protocol for manifold architectures. So in manifold year, a directory will be used to maintain coherence, but scalability issue arises because this directory can grow very large with increasing core count. So one potential solution is to use timestamp-based cache coherence, which eliminates the directory, in which every private cache line will have a predicted timestamp, which means after this timestamp expires, the line will be self-invalidated. So in order to maintain coherence, on the right, we know the largest timestamp of all the shares and wait until that expires, coherence is maintained. We can see the problem with this protocol in the long stall involving the writes, and the solution is our stall-free approach. Results show better performance and scalability. Thank you.
Hello everyone, my name is Lina from Georgia Tech. BLASTS is a set of level 3 basic linear algebra subroutine and compared with cuBLAST-ST. It demonstrates 26 performance gain and the communication of it is only 1/3 of cuBLAST-ST. BLASTS has a hierarchical TL cache built on multi-GPUs, which significantly reduces total communications. And BLASTS also has a synchronous task scheduling runtime, and it perfectly overlaps communication and computation on multi-GPU streams. And most interestingly, BLASTS supports backward compatibility. That means a multi-GPU library computes in a CPU fashion. And okay, that's the BLASTS is fast, communication efficient, and amazing to use. Thank you.
Hello everyone, I'm Amir Elkan from Simon Fraser University. I'm here to present the tools per use, So if you look at the traditional workflow for designing an accelerator, the process is slow, tedious, and infeasible for large different space exploration. So we'll develop a tool per use which can be added to accelerator design cycle and help the designer to save time and money investment. So per use is an end-to-end tool which highlight and classify the loops which are amenable for acceleration, and it helps